欢迎回来，我们来到 ELEC207第9课，我们来去测量一些瞬间的一些变化。那么我们说，关于一些材料啊，它会有一个动态的一些性质，就是说，所有的这些静态的 experiment 呢，它都会有一些这个，它这都是一个就是 steady state， 就是一个静态的，就我们就是一些这个。steady 的一个状态。那么我们接下来说一个动态的呢，它就是必须要会跟着这个，就是在这个 input quality is applied， 但是它那种静态那个状态在达到之前，但是 input 已经改变了那个状态，那就叫一个动态的那个过程中的那个变化。就像你把体温表放到你的身体里面，它的 input 已经变了，它的外界环境温度已经变了，但是它达到那个温度变化还需要一个过程。我们现在研究就是这个过程。我们呢就说明，我们通常呢有2个 input function， 我们通常要考虑，要么就是说这个stepped input， 就是或者是说一个正弦的一个 input。那么我们接下来说，我们说这个step general response 对于一个线性的 time invariant system step。to a step， 注意一定是一个 step change， 它可以被写成一个 an 就是 qn 的 n 阶导加上 an 减1乘以 qn 的 dn 减1次导加上 a1 乘以 dqn 比 dt 这1阶导再加上那个0阶导，它就等于 b 连 k q input， 好吧，就是 output 的n 阶导乘以n 阶导的系数，加上 output 的 n 减1阶导乘以 n 减1阶导的系数，巴拉巴拉乘以1阶导乘以1阶导的系数，加上0阶导乘以0阶导的系数，那么它就等于这个 qi 乘以 b0。那么 bi 就是它的quality， qo 就是 output quality， 然后 an 到 a0 还有 bn 它都是它的 coefficient。那么我们接下来说，它这是一个 n 阶的一个导数方程，它有一些 coefficient。那么这个 transition response 呢，可以被分成它的一个就是可以被 based on the order n of the equation。The transaction response can be classified based on the order， 就是你要么是比如说1阶 response、2阶 response、3阶 response， 还有0阶 response 啊。我们说最喜欢就是0阶 response。那么0阶 response 呢，它就应该是一个不考虑任何导数的吧？那么就是说它是一个它的a out q o 等于 b out 乘以 qi。我们说这个 q out 等于 b0 比上 a0 乘以 qi，which is equal to the k qi，where the k equals to the bn divided by an is the static sensitivity. This means that the output follows the immediate of the input. For example, the resistive potentiometer is a zero order system, which means that the moment you change the position of the potentiometer, and you can have the corresponding output of the changes. So therefore, it is a zero order system. And the response of the first order system can be derived by the following equation, which means that A1, the derivative of the Q out by the first order derivative of the Q out plus the A0 times the Q out, which is equal to the B0 times the QI. So therefore it will correspond to an exponential transition in the output follows a step change in the input. For example, the thermocouple is a first order system. The reason is that, everything when you comes into a temperature, it will come with the heat, right? And the heat will take the time for, nothing will have the infinite power. Therefore, the transformation of the energy will take time. Therefore, we must, just like the example I mentioned, you change the you want to measure the body temperature. Therefore, you must put the thermocouple into your body on the surface of your body for time. Therefore, and this is let's say this is the output. This is the input temperature change, and this is the corresponding output temperature change. Okay. So in general, the first order response arises from a single energy storage component in the system. Yeah, and the thing is that what if you have two energy storage, for example? I mean, what if it is RC circuit, which means there is only one energy storage component, which is called capacitance. Then you will have a first order system. And what if just A1 times the derivative of the Q, the first derivative of Q naught plus the A0 Q naught, is equal to the B0 times the QI. Then let's come to the reason why. That's the reason why. There's a very important thing here. We are here, okay? The general equation. The general equation will be identified as here, where the Q out T, which is equal to the Q0 T infinity plus the Q naught 0 minus Q naught infinity, which is correspondingly times the e to the power of t divided by tau, and the Q naught 0 is the initial value and the Q naught infinity is the final value. Okay, so the tau corresponds to time required to reach the 63% of the final output value, and the transaction can be usually considered ended as the 4 tau or 5 tau. Okay, so therefore I can, we can actually calculate. We can actually calculate what is the exact time that we need to put in our body to measure our measure our body temperature. So in order to know that, we just need to know that what is tau, and the tau is actually the so what is tau of maybe multimeter, and that's a very good question, isn't it? Yeah. So what is the body temp? What is the tau of how to measure the tau? Yeah. Let's ask a question. How to ask a tau? Oh, good. 我们又来问问题了。The learning resources discussion board, instrumentation, and start the trend. How to get the tau of a body temperature measure. I have a body temperature with 汞是什么？汞。哦 ，Hg， 对 ，with Hg。How can I know the tau of the body temperature? Which I can get the best time for measuring my body temperature. It's good, good. Hop, hop, hop. Blue. Okay, cool. And let's continue, okay? Okay. We are going to get the tau, and we are going to know how much time we need. Okay, cool. And additionally, we are going to talk about the reason why it is 60 the tau is the time to reach the 63% of the time of the final value. It's just that what if you substitute tau into the equation and you find that when this is infinity, it will be just the 1 and plus, and this is 0 minus 1 times the y is minus 1 times the e to the power of minus 1. Okay, e to the power of minus 1. E to the power of minus 1. Therefore, it's 1 minus e, which is around 0 points. Yeah. And what is 4 tau? It is, what if it is 4 tau? Then it is minus 4, which is minus 4, which is around the 0.0. 0.8. Okay, cool. So let's continue talk about the second order system, where it is the mathematical model of the physical interpretation. The second order system is followed by this equation, which is A2 times the second derivative of the output times plus the A1 times the first derivative of the output plus the A0 times the zero derivative of the output, which is equal to, and the summation will be equal to the B0 times the quantity input. So there are now two energy storage components in the system, which is a capacitor and an inductor, and the energy is exchanged between them. Therefore, the output characteristic may be characterized by the oscillation. The thing is that why it is oscillation? It is changing the energy from one to another and changing from another one to this one. Okay, and for example, it is spring and a damper. So what is the spring? The spring is just something that the spring is just something, how to say? The spring is just something, I mean, it will not change, okay? The energy will not disappear with the spring. But for damper, it will change. And you can just treat the damper as a spring with a fraction. Yeah, with a fraction. And let's say the F is equal to F is the input, and it can be corresponds to the second derivative of the mass, and the first derivative of the damper, the first derivative of the time, which is corresponding to the damper, and the zero derivative of the spring. As we can know that the F equals to ma, and the damper maybe it's like the lambda kV, and maybe and we all know that F equals to kx, right? So therefore so the F is the input and x is the output, corresponding output. Okay, and then the second order differential equation can be written as this, which means what is the natural frequency? What is the natural frequency here? And what is the natural frequency here? How is the natural frequency comes into play? And let's ask him. What is and the static sensitivity. Yeah, K is still the same, right? K is still the static sensitivity. It's underdamped or overdamped. Okay. And the epsilon is how do we measure the damp rate? Ha, hu, ah, hu. And the thing is that the damping rate can be the natural frequency include as the square of the A0 divided by A2, and the 这个东西 is called C, I think. It's equals to the omega n times the A1 divided by. How can you explain the linear relationship between the damping ratio and the frequency? Or between the natural frequency and the damping rate.它有一个线性的关系，虽然我也不知道它什么关系。然后它的这个 second order system 它就有3种情况。如果你是一个如果你是一个这个 input 是一个 unit step 的话，它会有，如果当你的这个 epsilon 它是这个符号他妈到底什么意思？怎么读？
They were often low.
开机。这个叫伊布斯龙 ，zeta。C 哦，叫 C， 叫 C 叫 C。这叫 C， 伊布斯龙是那个小 E。
Xi is the 14th letter of the Greek alphabet. It is pronounced Xi in modern Greek, and generally or in English. In the system of Greek numerals, it has a value of 60. Xi was derived from the Phoenician letter Samek. Xi is not to be confused with the letter Chi, which gave its form to the Latin letter X. Greek. Both in classical ancient Greek and in modern Greek, the letter I represents the sound, KS. In some archaic local variants of the Greek alphabet, this letter was missing. Instead, especially in the dialects of most of the Greek mainland and Hivaea, the sound, KS was represented by I section. Because this variant of the Greek alphabet was used in Italy, the Latin alphabet borrowed I section rather than I as the Latin letter X, Cyrillic.
Hello, this is Pastor Stephen Anderson from Faithful Word Baptist Church in Tempe, Arizona. Here to teach circle from one side to the other. So this is the letter gamma. So alpha, beta, gamma, and then after gamma is delta. Now delta looks similar to an English D, but it has this curvy thing going on. To me, it kind of looks like one of those bombs, you know, the little black round bomb with the wick coming out of it. So this letter is delta, and it is basically pronounced like the TH in the word the, okay? If you speak Spanish, you're probably used to pronouncing the D's in this way. But this is delta. So alpha, beta, gamma, delta. All right, and then after delta, we've got epsilon. And epsilon looks very similar to an English E, just two little loops like that. That's the lowercase epsilon. And epsilon makes the eh sound. Now remember, the Greek alphabet the first sound of the name of the letter tells you what sound that letter makes. So alpha says A, beta says V, gamma says G,
Gamma.
delta says V, and then epsilon says epsilon.
Epsilon.
Now, the good thing about these vowels is that they only make one sound.
Epsilon.
Now, we'll talk a little bit later about combining vowels into diphthongs, but epsilon basically just makes one type of a sound. It's not like in English where we have these dramatically different sounds, E, A. It just makes an as an epsilon. Sometimes it'll be longer, like A. I mean, but it's not that big of a difference. So after epsilon is the letter zeta, and zeta has a little loop thing at the top, and it swings out like that and comes back. So it kind of looks like a C, but it's got these other decorations on it. So again, the zeta, you just start at the top, make a little loop, and then make a big giant loop, and then come back like that. That is zeta, okay? Then after zeta, you have the letter eta. Now, eta is basically like an English lowercase n, but then the front just comes down a little bit further, okay? So it's like you're writing an English lowercase n, but then you just come down a little bit further. This letter is pronounced eta. So we have zeta, and then we have eta. Zeta says z, and eta makes an e sound. All right? Then after okay, so basically you start out writing in elementary school. This is what they taught me, all right? Now the next letter is pretty tricky. It is called ni, okay? So we have ni and ni. Ni looks just like an English lowercase v, okay? So when you're reading something in Greek and you see this letter, you're going to want to pronounce it like a v sound, but it doesn't make a v sound, it makes an n sound. This is ni, ni. So you got to get used to pronouncing this as an n, ni. This letter makes ni. After ni and ni, we have si. Si is basically the X sound, and this one you start out with a little loop at the top, then you make two big loops, and then you come back like this. So it's almost like a backwards 3, okay? But it has some other little frills going on here. So it does resemble a backwards 3. So you start out by making a little loop at the top, and then you loop down, and then another loop in the middle, and then you come back at the bottom. Now this
操，都不会写了，我操！练那么长时间的，操！我操，这东西怎么写？操，不会。
This letter was actually pretty easy for me as pop. It's a little bit fast. And he's got and lump. Triple here, zeta, eta, theta. And then we've got iota, kappa, lambda. Then another nice rhyme of these 5. Mi, ni, si, omicron, p. And we have
应该就叫 C， 这东西就叫 C， 不管了。对，没写错，放空自己，重新写一个啊，不要怕，这东西就叫 C 的，不管了，或者叫啥 C， 不怕，这不是这样呀！操妈的！妈的，不会写了 C。
So this letter is phi. Then after phi, we have he. Okay, and this is basically like the ch in German, if you know how to.
我操，晕菜了！这叫 C。How to write a C?
C.
牛皮。是这意思吗？ 哦，想起来了，对对对。啊，对对对对对。嘿哈哈哈哈哈哈哈哈！对对对，就这样，好了，就这样，这叫 C 啊！操，这东西叫 C。对，就叫 C 了，好吧 ？C， 啊 C， 好漂亮。好，对，没事，不好意思。那个，反正这东西叫 C， 好吧？这东西叫 C， 啊，这个 C 呢叫 damping rate， 好吧？那就这样了。然后呢，我们接下来说这个如果它小于就是under damping， 就是它的那个震荡不是很强，好吧？就是它震荡的不是很强。那么如果这东西大于1的话，那就是震荡的非常强。我们通常就要让它under damping 一点。这个 under damping 一点的话，它就会这个 overshooting 啊，就让它稍微让它0.6到0.8左右比较好啊，就让它那个 damping rate 0.6、0.8左右啊。然后它为什么要 overshoot？ 就是让它就是力量大一点，让它 under damping 一点。under damping 就是动的，它的不好的地方就是，比如说电压它突然会在那个稳定电压的，比如说比它的稳定电压100还过50%左右，但是呢它的那个好处就特别快啊，所以说就是你先做多一点，然后再往下一点，再回一点，你会让它变特别快。但是就我以前做事情的方法是没有问题的，只不过是它稍微快一点。但是呢，你要是一点一点往这边趋近的话，可能会更慢。对，那么所以说这个如果 K 小于1的话叫 under damping rate，under damped， 你就想小的东西叫 under 嘛，大于1叫 over damped 就完了。好，然后那个这个 damped 是跟那个就是摩擦系数越大，你想啊，你的那个摩擦系数越大，它越难推是吧？你的位移就应该越小，对吧？但你的那个你如果摩擦系数越大，你一开始一下子给你推得好远，对吧？一下子给你推的那个好远，但结果你又推回来了，对吧？那个弹簧给你弹回来了，然后又推得好远，又弹，最后达到一个稳定的一个状态，所以就特别神奇啊。好，然后这个就这样，非常感谢大家。